So we've seen that the limiting value of the slope basically with respect to the y direction of this segment is what we're going to call the partial derivative of f with respect to y at that point. So this is a partial derivative of f with respect to y at the point x naught, y naught. Just as with a function of a single variable, we can use rules of differentiation to calculate partial derivatives. Okay, this is actually a fairly simple process. Remember that we used as an example the function, and make sure we're on the paper here, f of xy equals x squared y plus y sine of x. Now, if we're moving in the y direction, the value of x doesn't change. There are theoretical considerations. We have to develop the theory behind this process. We have to understand when this limiting value will occur and when it won't. But we'll just say for now that for any function f of xy that we can write down using most of the functions that we're familiar with, as long as we don't have a denominator that goes to 0 or a square root of a negative, now we're going to be able to take our derivatives. And that's the case for this function. We would say this function is continuous and differentiable everywhere. We'll see what that means, but let's just calculate it. And this is easy to calculate. Since x doesn't change, treat x as a constant and take the derivative. Then the derivative that we'll call f sub y of xy is what? Well, it's x squared times the derivative of y. X squared acts like a constant. The derivative of y is just 1. So this is just x squared. Now I don't like that particularly. I'm going to change this function. I'm going to call this, going to make this x squared y squared. Nothing we've done depends on the function that we wrote down the first time. And let's go ahead and make this y a square root of y, just so we have clear connection between the function and the derivatives we're going to take. Now, treating y as x as a constant, the derivative of y squared with respect to y is 2y, so we have x squared, basically a constant, multiplied by 2y. The derivative of the square root of y is 1 over 2 square root of y. And since we're treating x as a constant, sine of x is just going to be a constant. So there's our y derivative. If we want to know what the rate of change of this graph is, if we move in the y direction starting at a certain point xy, we just plug in the coordinates, the x and y coordinates, evaluate this, and that tells us how quickly the function is going to change as we move in the y direction from that point. There's another notation for this. Just as we use d dt, for example, to take a derivative with respect to t, we're going to use lowercase Greek delta instead of d to indicate that we're taking a partial derivative with respect to y. This indicates that the function of which we're taking a derivative is a function of more than one variable, and that we're considering only the y as variable in the process of taking this derivative, treating every other variable for the moment as constant. So this would be the partial derivative with respect to y of the function f of x, y, or partial of f of x, y with respect to y.